Thank you, Rafael. And also, thanks for staying for the last day. And before I start, I would also like to thank the organizers, Jose and Eric and Victor, for including me. And although I don't know Eduardo, happy birthday. And thank you for including me in this very nice family-like community for this week. I really enjoyed it. This was my first time in Brazil, actually. And I had a lot of fun. Thank you. So yes, as Rafael was saying, I will talk about, can you actually hear me? So? Okay, I will try to speak up. I can't speak very loud, but okay, I will try my best. Okay, so yes, as Rafael was saying, I'm going to talk about band topology of triplet excitations. Right, so throughout the week, we heard a lot about topologically non-trivial band structures, and therefore I will not go into too much details, but let me just, start somewhere, and I guess like it all began, in any case, with the discovery of integer quantum Hall effect and Haldane's model that realized churnful bands without the inclusion of large magnetic fields. And since, topologically non-trivial band structures are in other systems as well, that include, instead of the electrons, bosonic particles like photons and phonons. And what we are interested in is when this actually is happening in magnets, in fact, in the excitations of different magnetic systems. For example, if we just take a simple ferromagnet that is topologically actually trivial, and we think about the magnetic excitations of this system, which corresponds to a spin flip, that can then propagate over the lattice and form bands very similar to electrons, then we can ask the same questions as we would for the bands of electrons, like what is the topology of these bands. And as it turns out, the Haldane model is actually realized pretty easily in these systems, because if we just consider, like, for example, the simple ferromagnet with a Heisenberg interaction and take into account some anisotropies that are naturally present in most of the materials. For example, the Jarzynski-Mourier interaction that is also known as the antisymmetric exchange interaction. This can actually give rise to non-trivial band topology. And actually, when you do linear spin wave theory, then these type of terms will give exactly the type of complex hopping amplitude that we need for realizing these churnful bands. And then, of course, because these magnetic excitations are neutral particles, right? They don't have an electric charge. We will not have something like the quantum Hall effect, but instead, because they carry energy, if we apply a temperature gradient, we can have thermal Hall effect, and that means that we put, for example, a temperature gradient across the sample in one direction, and then measure a transverse heat current perpendicular to that. And of course, this is not going to be quantized because these are bosonic particles that we will, these bands will be filled thermally and not like, in the case of the fermions. Right, so what happens if we add spin degrees of freedom? Then we can realize, other interesting topologically non-trivial band structures, for example, the Z2 bands of a spin Hall system. And then in that case, we can have, quantum spin Hall effect. And then, the question is like how we can have something similar for magnetic systems and magnetic excitations, because a spin flip is kind of, it's really neutral. It doesn't carry like a spin, sort of. Like it's a flavorless particle. The first proposal for magnon quantum spin Hall insulators came from Katsura-san's group, and they proposed a bilayer system in which the top and the bottom layer are polarized in the opposite directions, and therefore a spin excitation, for example, in the top layer would be an upspin, and a spin excitation in this bottom layer would be a downspin. So if these are antiferromagnetically coupled, then we have two types of spin excitations. And of course, because the Jarzynski-Mourier interaction has opposite signs and affects these excitations in a different way, they would deflect into the opposite sides of the sample and create a spin separation very similar to what we have in the quantum spin Hall case. And then, of course, one can measure a spin Nernst effect in these systems. That's like the proposal for these systems. Right. Okay. So here I was saying that I'm going to talk about triplet excitations, which are very similar like magnetic excitations, but instead of having an ordered magnet, we have a magnetically disordered singlet ground state, and then for those, a triplet would be the excitation. And these are actually interesting because, first of all, we don't need like, explicitly bilayers for example, if you wanted to have some kind of a flavor for our excitations, because the triplets are naturally a spin 1 particles, so we have 3 flavors for them, and we showed in our previous work that they can actually exhibit churnful bands, and also maybe are good candidates for Z2 band topology as well. Right, so as part of this introduction, let me just go back to our previous work on the strontium copper borate, which is the Schwarzschild Sutherland material. And then in this system, the copper ions are occupying this orthogonal dimer lattice that is the quasi two-dimensional lattice, and we have the A and B dimers in the unit cell. And if we wanted to have just like a Heisenberg model describing this material, then actually this is what we would expect in the ESR and neutron spectrum. Right? This would be like a fully SU2 symmetric Hamiltonian, and in the ESR spectrum we would have like this 6-fold degenerate modes at 0 magnetic field that would be then Zeeman split, and we have the 2-fold degeneracy because of the 2 sublattices. Right? And then the neutron spectrum would be pretty boring. It would be actually a flat band that is 6-fold degenerate, because if we look at the symmetry of this lattice, if we have just singlets as the ground state and the triplets are the excitations, because of how they transform, how differently they transform under different symmetries of this system, like the mirror symmetry that we have, actually hopping of the triplets would be forbidden. And we would not have hopping matrix elements, so this would be completely a flat band. But this is not what we see. In the experiment, in fact, what we see is that these bands are split, and they are dispersive, and this same splitting is actually there in the ESR spectrum at 0 magnetic field, and then of course it's all the way down in the magnetic field as well. So that indicates that actually anisotropies are important in these materials, and without anisotropies one cannot really describe this system. And if we take those into account, and after some math, one can just like write a Dirac-like Hamiltonian for these triplet excitations, for the hopping of these triplet excitations, and that consists of a constant term and a D vector that is like a pseudomagnetic field, right, in the momentum space that Zeeman splits the spin 1 triplet. Right, so this L is a spin 1 operator. These are actually 3 of the Gell-Mann matrices that form an SU2 subalgebra of the SU3, and then one can actually think about it as kind of like a generalization of the Dirac Hamiltonian into a spin 1 Dirac physics. And that's, this is what the band structure looks like. As it turns out, one can use magnetic field to tune the system and to go into a topologically non-trivial band structure. So when we are here, it's actually very small. I'm sorry, I should have zoomed in. But like when the field is very, very small, like less than 1 Tesla, then we have these topologically non-trivial bands. And this point here, when the bands are crossing again, is actually a topological transition from the non-trivial bands to the trivial bands. So that's kind of like a Dirac cone already measured in the ESR spectrum. All right, and then if you look at correspondingly an open system, then of course we would have edge modes, and because these are larger spins, so spin 1, we have larger Chern numbers plus and minus 2, and then correspondingly 2 edge modes that are propagating in one direction and 2 that propagate in the other direction. And later there were, this neutron spectrum was measured again, and this is very nice work by Paul McClarty and Radu Caldea. They showed also that bound states of these triplets are also important in this compound, and they also contribute to the non-trivial topology. All right, so much about the Chern bands, and let me also kind of like flash this, work on the Z2 band topology realized by triplets. So this idea came first from Andreas Schniederskub, and we were also thinking about something similar at kind of the same time. And they worked on the honeycomb lattice. We decided to use the Kagome. It actually doesn't matter. It's a toy model. And what we wanted to kind of investigate is like how protected these triplet excitations, or like the Z2 band topology of the triplets are really, because as you know, these are bosons, and we don't really have like that time reversal symmetry and the Kramer's degeneracy, right? So then this was kind of what we wanted to see. And of course, as long as we are working in like kind of with a toy model, as was first proposed by Andreas Schneider, we actually can get Z2 topological bands and these helical edge modes and so on, and kind of like a Z2 index is a spin churn number that would characterize these triplet excitations. So here, what you see is that we have the three usual Kagome bands, and all three of them are threefold degenerate with the triplet flavors. And of course, as soon as we have Joule-Shinsky-Mori interaction, then only two of them will actually be degenerate, the SZ plus one and SZ minus one triplet that are time reversal partners, and they have opposite churn numbers, so they will give this finite spin churn number, right? And right, so in fact, what we wanted to see is like, what is the pseudo time reversal operator that squares to -1 and can protect the Z2 topology? And as it turns out, this requires a U1 symmetry in the system. Oh, sorry, I don't know what I did. Super. Okay, right. So we require this U1 symmetry and also the time reversal symmetry. And as soon as either of them is broken, the Z2 band topology is lost. And as it turns out, in real materials, this actually is almost never the case. So like almost all the time, we would have some kind of an anisotropy. In this case, for example, the symmetric exchange anisotropy that will actually destroy the U1 symmetry, and together with that, the Z2 band topology as well. So these are not really stable, unfortunately. Right. So okay, with that, we were curious, like, can we have other types of topologically non-trivial band structures? And we went back to work on like real materials like the strontium copper borate was, and set out to investigate this family of monoclinic systems, where one of the members is the potassium copper trichloride. So this is a 3D material, and we were first like curious whether it can have something like a higher order topological insulator or something like that. But unfortunately, it's not. But it's still interesting, and it gives interesting topological non-trivial band structures depending on what kind of anisotropies are there in the system. So this work has been done by my students, Charles Walker and Matt Stern, who are sitting here, and also they had a poster about this, so maybe you already know the story, and in that case, I apologize. Or maybe I will just repeat it one more time. Right. So what I will say is like, is actually really their contribution. So if there's a mistake, that's my fault. And if you like it, that's because they did an awesome job. So, right. Okay, so potassium copper trichloride, as I said, is a monoclinic system, which you can think about. It was actually for a long time considered as kind of like a dimer chain model, and in which these chains are like weakly coupled. But in fact, as it turns out, the coupling between the chains that you can see here, these are actually along the A direction, and the coupling between them is quite important from the elastic neutron scattering. Okay, so about the structure, we have these double chains, as you can see in the BC plane. Right, we have two types of chains. One is like oriented in this direction, and the other is oriented in this direction. So we have like this doubling in the unit cell, very similar to the Schrochter actually, the Schrochter-Sutherland, except these are not orthogonal to each other. They have like some sort of a different angle. And then these coppers are sitting in a edge-sharing distorted octahedral environment. I don't know why this is happening. I'm so sorry about that. Right, this octahedral environment, right, and then there is a very strong interaction along this copper-chlorine copper path that is in the short basal plane of these octahedra, and then there are weaker interactions along the chain and also between the chains. Right. Okay, so the symmetry of this system is actually very low. We have inversion on the dimers, so in the middle of the dimer, the two types of dimers, and also it's not really visible, but also on this magenta bond here. And we also have a mirror plane, sigma b, that is paired with a half a translation in the B and the C directions. So you can kind of see it from this picture maybe that once you apply this mirror plane, then the A type of dimer will go into the B type of dimer, and then you have to shift it with these half lattice constants to actually map it back into the original lattice. And also, very similarly, we have a C2 axis about the B axis, and then that's also a non-symmetric symmetry. We need these half translations. Right. So this is some early experiments, and surprisingly, these are actually the experiments. So like after like 20 years, there has been no new measurements on these materials. All of these, like this is monetization. As you can see, like below about 20 Tesla, there is no monetization whatsoever. And then in the ESR spectrum, we see the spin gap very similar to the strontium copper braid, and also the same spin gap is present in the inelastic neutron scattering. And that's all consistent with a dimer singlet ground state and triplet excitations. So this is our starting point. This model, so like as I said, 20 years ago, when these measurements were done, has been investigated with a Heisenberg Hamiltonian. And that's a fully isotropic Hamiltonian that can actually describe quite well, these excitations. The solid lines that you can see here are in fact those theoretical calculations for the neutron spectrum. So this is actually where we start. We begin with this Heisenberg Hamiltonian, and I'm sorry, there will be a lot of interactions, so I apologize. Please bear with me. I will try to be slow, but it's going to be vexing. Right, okay, so we have the J naught, which is the interactions on the dimer, and then these different J's, where the index is actually denoting the direction in which the dimer is actually located. So like the JEBC are this, like the red and the gray direction that connects the different species, the A dimer with the B dimer. The JA is along the A direction, along the ladder, the chains. And the JE2C is this magenta bond that connects the same type of dimer, so the A with the A and the B with the B. And so these ones will not have Jarzynski-Maury interaction, and neither the dimer, but everywhere else, those are actually going to be allowed. So in fact, if we look at the symmetries of this material, then there are all kinds of interactions that can be present, like the 15 different parameters per bond, except when there is inversion symmetry, because then there is no DM, but other anisotropies like the symmetric exchange are still allowed. So it's actually quite surprising that this model can be characterized by Heisenberg Hamiltonian, when in fact the symmetry allows all of these different anisotropies that have not been taken into account before. And so what we actually did first is to derive the symmetry allowed Hamiltonian, and of course not all of these parameters will appear. Like if you write, for example, a spin wave Hamiltonian, a lot of them will actually just appear like as a combination. So they're not all independent. At least we don't have information independently about them. Right, so what we take into account is the usual Heisenberg Hamiltonian, and then the Jarzynski-Maury interaction, the symmetric exchange, and the Zeeman term. Right, so to actually keep our sanity, we forget first, we try to do a systematic analysis, and we forget first about the very unimportant anisotropies, and because from the symmetries we know that the B axis is kind of the important axis, we keep the B component of the Jarzynski-Maury interaction, and we set the magnetic field in the B direction, and forget about everything else in the first step. And in that case, as one would expect, if we write the Hoping Hamiltonian for the triplets to describe the dynamics of them, we actually have still a U1 symmetry, because we just have one axis. We selected the Y axis, or the B axis, in the system, so that means that there is still a U1 symmetry in the system, and then the SY +1, 0, and -1 triplets are completely decoupled from each other. And so we have these three Hamiltonians that are completely decoupled, and we can just diagonalize them separately, and they all belong to different SY sectors of the triplets. Right, and that actually is very useful, because this is going to be our starting point, and then we're just going to describe each of these sectors with a Dirac Hamiltonian or Dirac-like Hamiltonian, right? And then that's easier to analyze, very similarly to the Shostri and Sutherland, right? So we have this constant energy shift, and then the components of these D vectors are like this. Of course, the Jarzynski-Maury will couple to this M parameter, which is just the Y component of the triplet. So it's 0 for the SY0, that we don't have Joule-Schwinsky-Moria whatsoever. And then for the plus and minus 1, this is plus and minus 1. Right. So we have a 0 Z component, and that immediately kind of suggests that there will be some degeneracies in the system. Right. So if we just use these, the parameters previously derived or like previously determined from the neutron, fitting the neutron spectrum, we can actually calculate with this simple Hamiltonian the band structure, and it looks pretty similar to what has been measured. So this is kind of like a good, effective Hamiltonian for the triplets, although it's very, very simple compared to like if we wanted to do the full like triplet wave or bond wave analysis. Right, and then now we want to see what's the effect of the small anisotropies. Right, and this DM vector is actually, so the D vector will contain all the information that we need to know about the topology. And when the D vector becomes 0, the bands are touching, and one can actually determine very easily where those touchings are going to be. So these are nodal lines in the band structure of this system, and we can calculate the topological index by looping around these nodal lines and integrating the Barry phase, right? And then we get a pi. So this is actually very promising. And then also one can plot, the band structure and then see like for these different cases in momentum space, we really have those degeneracies in the triplet band structure, right? So the question is like, of course, yeah, sorry, I'm running ahead. Like this is the same thing for an open geometry when we have a finite system in the B direction, and we just plot the spectrum along like this irreducible wedge in the Brillouin zone of the AC plane. All right. So and then as you can see, between these touching points, we have surface modes that are collapsing the gap. And the question is like, okay, so if we include additional anisotropies, what will happen to this band structure? And in fact, there are a lot of different terms that one can include, but please take my word for it that most of it are pretty boring and nothing will happen. They will just renormalize these coefficients that we have, that we have for the y and the x component of this D vector. And what actually will give rise to the Z component is if we tilt the magnetic field away from the B direction by like a small angle. And we also include some of the asymmetric exchange anisotropies. And our hope is that maybe we can like, aside from this nodal line phase, we can maybe have like Y points or even fully gap out the system and have like churn bands and stuff like that. And so this is what we try to analyze systematically, and I don't know how much time I have, maybe 10 minutes? Okay, cool. So that I can be slower, right? Thank you. Right, so first, what we want to take into account is on this purple or like magenta dimer, the DM interaction, as I said, is not allowed because it's an inversion center. But we can have a symmetric exchange anisotropy, and that's exactly what this Ka2CX is. Right, so we will take into account that anisotropy and also a similar symmetric exchange anisotropy on the dimer. So the dimer is also an inversion center. There is no DM on the dimer either, but we can have the symmetric exchange. And what happens when we tilt the magnetic field and then take these into account, these are actually small parameters. But as you can imagine, my original big Hamiltonian that was block diagonal is not going to be block diagonal anymore. These terms will actually mix the different SY components of the triplets, but one can do something like a canonical transformation and get rid of, like these couplings and somehow take them into account perturbatively and still keep, like this sort of SY plus minus 1 and 0 basis. And that's exactly what we do because we want to keep this simple Dirac type of Hamiltonian. So we do a canonical transformation to include these additional anisotropies. And that will actually show up in the Z component of this T vector. And once we plug in again our criteria for the vanishing X and Y component of this D vector, then we see that this is what the D vector looks like now when we have those anisotropies. So of course we can't satisfy both of these conditions simultaneously, but depending on what is the size of these anisotropies, we can still fully gap out the system, or like either have a fully gap system or have some degeneracies. Right, so for example, when symmetric exchange on isotropy, the kx, is the same as the symmetric exchange on this magenta dimer, then this d vector vanishes along these blue lines, right? So then here we have a degeneracy, and similarly, if they have opposite signs, then we will have a degeneracy along this red line. And this is kind of, I'm not sure, it shouldn't be called a phase diagram, but let's think about like this is the parameter space that we are investigating, right, when we parameterize this K-A2CX and the KX with the sine and cosine alpha. And depending on the size of this alpha, this is kind of like, either we have degeneracy along the original blue lines, or we have degeneracy along the red lines, or when we are in between, the system is fully gapped. So the pink and the gray areas are when the system is fully gapped, right? And as it turns out, the gray areas are trivial topologically, and the pink areas are topologically non-trivial. So depending on the size or the ratio of these anisotropies, we can actually have Chern bands in this material, right? And one can actually see that, for example, setting this angle to be 0, so we have only the kx anisotropy. Then if we plot, along, of course it's a 3D material, right? So we can only plot like skyrmions along some cuts, and so these are, the skyrmions, or the lack of the skyrmions in the BC plane, in the AC plane, and the AB plane, in the Brillouin zone. And as you can see, like I think maybe it's most clear from here that this is not a skyrmion. And one can, of course, make a correspondence between the skyrmion density, and of course the skyrmion is formed by the D vector, right? So we are talking about the momentum space, and we are plotting the D vector in the momentum space, and that like for different points in the Brillouin zone. Right? And that can be brought in connection, this skyrmion density with the Chern number of those bands. Right? So depending on whether we have a skyrmion or not, this is going to be a trivial or a topologically non-trivial band. Right. Okay, and correspondingly, if we open the system up, again, along the B direction, as we can see, these surface modes are fully trivial. They don't collapse the gap whatsoever. Right? So this is also in correspondence with that case. So then we can go to this boundary when we are on one of these, like in this case, the blue nodal lines are still there. And then as you can see along these lines, we actually have a vanishing D vector. So those are these white points in the figure where the D vector is actually 0. So I can't really plot a vector there. Right. And then in this case, as you can see, these degeneracies are actually surviving. So we have a nodal line type of a phase. Right. And then, going further, we actually now form skyrmions with the D vectors, and in an open system, we have non-trivial edge modes. Right. So depending on really like what is the ratio of these parameters, a lot of things can happen in this material. Right. Okay. So now, right. So like the question is like, can we actually go between lines, because we only had like fully gapped system and nodal lines, and can we have nodal points, for example, or Y points in this system? And for that, actually, we need to include another anisotropy. So in this case, instead of having the symmetric exchange on the dimer, we can have it between the dimers in the A direction. And that will give a new condition, right? Like this, then I will have here in the Z component KAX times the cosine K, which is a new condition for the momentum. And to be able to zero this D vector out, right, I need to satisfy that the DZ component is actually going to be 0, and that gives us another condition for the KA component, which now, instead of forming a line, we just have like certain points in the Brillouin zone where this D vector can be 0, and that one can plot it in many ways. So this maybe is not the best plot, and I apologize for that. But so the red and the magenta lines are solutions to this case, and the blue and this lighter blue are solutions for the bottom case, for these arc cosine or like solutions for the Ka. So what you can see here, this is the Ka value, and the alpha parameter is along the Y direction. So as we change the alpha, we will have like different solutions where we have in the momentum space those nodal points, and then of course we have regions when there is no solution. And that means that in those regions, for those alpha values, we actually have a fully gapped system. There is no degeneracy whatsoever because this D vector will never become 0. Right. And again, we have a similar, let's say, diagram for this parameter space. And now the pink region is, again, the ones when we can't satisfy these conditions and the system is fully gapped, or all of the bands are fully gapped. And then the white region is when we have actually while points in the system somewhere, right? Okay, so then, this looks something like that. So this was like the dashed lines. I don't know if it's actually visible or not. These used to be our nodal lines, and then, of course, it's not surviving. So there are just like points where we will have the degeneracy. And then, of course, we can investigate like what happens, if we just start from alpha equals 0, so we are here, then we have, one can, of course, calculate the Chern number. For example, if we go along the Ka direction, right, then we will find that it's actually trivial. And then as we move with this alpha parameter, so we kind of like change the ratio of these parameters, right, we will have different, at different positions, our nodal points, and between them there will be like, the Chern number can actually change. Right, and this is what we are showing here, right? So like moving in this parameter space, right? We literally just move the plane where these nodal points are along the Ka direction, and that means that whenever we cross a plane where there is kind of like this touching point, then there can be like a topological transition. It's kind of like having the 3D material cut like in, like made of like series of 2D systems, and then whenever we hit a point when there is some kind of a degeneracy, then the Chern number can change, and that's exactly what you can see here in this figure, that the Chern number changes as we move along the K direction. Right, and then of course we can hit this point when kind of the two nodal points become or like be in the same plane, and then at that point we leave this phase behind, and we actually go to the, sorry, I think I skipped one slide. Maybe I didn't. Right. We can go into these fully gapped phases, and then the Chern number, of course, will not change its value. It will be just topologically non-trivial. And accordingly, of course, we would have these the fully gapped bands with non-trivial surface states in the open system. And that's kind of what I wanted to say. So to summarize, we think that this family of materials like the potassium or thallium copper trichloride are actually maybe more interesting than they were first believed. And if one takes into account the different anisotropies that can be present by the the symmetry of this material, then these triplet excitations may actually realize while nodes and nodal lines, and maybe depending on the size of these anisotropies, Chern bands, and so on. So there are a few open questions that we are still working on, and this is, we're trying to write this up and answer these questions, and so on. But yes, thank you so much for your attention.
Questions?
Thanks for this very nice talk. So just in your band structure, it seems like all the three spin sectors are completely separated. There's no overlap in the bands, right?
Yeah, so these are fully Zeeman split. Of course, it's much harder to analyze the spectrum when you don't have the large magnetic field in the y direction that Zeeman splits the bands, because then you have a lot of other degeneracies that may, they are harder to understand. And in this whole derivation, right, I don't know how to actually, maybe I will try to go back here. Oh, mine, okay, cool. Thank you, that's maybe easier. Right, this whole idea is starting from here, that we can somehow write this Dirac Hamiltonian for the triplets, because we have these fully decoupled subspaces, and the kind of the parameter that governs that is the magnetic field in the y direction that will Zeeman split them. So this is kind of the large parameter, and I cannot even do a canonical transformation, right? If I don't have this large parameter that somehow separates my different blocks from each other. And like that's the idea that the perturbations are actually smaller, the isotropies are smaller. If not, one can still do the full bond wave formalism. We won't have like a closed, like Dirac-like Hamiltonian in that case, but one can still, calculate Chern numbers and stuff. And this is actually what Charles was doing. So we solved the whole problem first, like numerically, and analyzed it like that. But then we thought like maybe having some toy model that describes it is nicer. So we just restrict ourselves to this higher magnetic field when everything is fully Zeeman split.
So another question is, you show some experimental data, right?
Yeah.
And it seems that there's clearly a nodal line in the neutron scattering data as well, right?
Yes.
But you know which spin sector it belongs to?
So in the neutron spectrum, there is no magnetic field. So all of them are fully degenerate, everywhere in the Brillouin zone.
Oh, I see.
And the splittings are probably very small. So this was actually the case for the strontium copper barrate. The first neutron spectrum didn't show the splitting from the DM interaction because it was just too old and the resolution wasn't good enough. And I don't know actually if, like how big the DM is. The ESR spectrum, if you look at it, at least, from this earlier measurement. Let's see, where is that? So they actually, I'm not sure how visible it is. It's very misleading. It's not this gap, the DM. It looks like it is, but it actually isn't. But this A mode here that is on the bottom, it has a double peak structure. And they say that this is actually coming from the Droshinsky-Mori interaction.
So I have one last question, sorry. But you in your final parts where you show the nodal points,
Yes.
So the nodal lines are still there, right?
No, those are so you kind of adding these additional isotropies, you kind of open them up and you have just points.
Okay.
They reduce to points in the Brillouin zone. Yes.
Thanks.
Thank you for the questions.
Oh, Judith, nice talk. Can I ask you about, so you have some certain cases, there's Chern bands of these spins, right?
Yes.
So given that they're bosons, and you mentioned thermal Hall effect,
Yes.
so do you have to do an AC measurement because you can't fill them? You have to, they will just go to the bottom of the band, so you'd have to go at some finite frequency to observe?
Right,
or?
so that's exactly the reason why the thermal Hall is not quantized, right? Because you thermally fill these bands, and you would probably just have contribution from the bottom of the bands. And most of the time, it's actually the Berry curvature is really located where you had where you were supposed to have the degeneracy, right? So like when you open the system, right, then the Berry curvature will be actually close to the touching point and not at the bottom of the band. So these are actually very hard measurements to do, especially in the gap system, because you need to actually be at higher temperature, let's say, to actually fill the bands somewhat. Yeah. Thanks for the question.
I guess I have two questions. One is when you these nodal points at the end, there's those you calculated zero field, correct? Zero applied field?
The which one, sorry?
The nodal points that you got at the end are in zero applied field.
No,
No,
they are
a big field.
in big, yes.
And then as I change the field direction, of course they come and they go, right? Or are they always there for all field directions?
Right. So yes and no. Right, so we have a large field direction in the B direction, and we just tilt a little bit. That's still a perturbative parameter, the other, the tilting from that field. We didn't look at what happens if you fully tilt or you tilt really far away from that, because then this description becomes.
But is there some kind of a transition then where, these, as you go around?
Yes,
so
I think, yes, probably there is.
And so what it would mean that if you did a ESR experiment as a function of field direction, you might actually see these degeneracies disappear.
That's a very good idea, I think, yes. You probably would see. And I think, I don't know how, okay, so this is a really, really old measurement in terms of measurements, but I don't know what, the resolution, I don't know how good this is, but even the splitting here, and to tell whether this is actually degenerate or split is I think hard to tell. I don't know how, well it could be repeated or, how feasible it would be. But
the other question I have is did you do any slab calculations to see essentially what the extent is of the edge states? In other words, how much?
Yes, so Charles made some calculations like that. I'm sorry, I don't have the plots here, but they, yeah.
Well, I just would like to know. I mean, for the parameters that were chosen, I mean, how many spins? This is an experimental question, of course. Is how easy would it be to see these edge modes?
Right. That's a very, very good question, and that's the problem with magnetic excitations. That it's very hard, I think, to measure the surface. If you know how to do it, I would be so happy.
No,
to
we
learn.
do know how to do it, but we need to know what the moments are, and of course that has to do with the healing length.
Right. I don't know that by
for-
heart. I'm
for
so sorry.
these- for
But how do you measure actually the surface? Because the neutrons measure the bulk, and even like a small angle, I think it's
So
very
you don't
hard.
have to do neutrons.
How do you do it?
You can do X-rays.
You can do it? Wow.
Yeah.
Okay. Cool.
But the question is how big is the how
Right.
many spins are involved? And in other words, it's not just a single layer at the surface.
Right.
There's a lambda. There's a healing length that goes into the thing, but you don't.
And
know.
you can separate it from the bulk?
Well, I'm asking you the question.
But I don't know. I don't know.
If it's big, look, if the healing length is big enough, then there's a large number of moments that are involved with the
Right.
spins at the edge, and then it's easier to see.
So
If
what
it's only
is-
a single layer, it's harder to see, but I need to know what that length is.
Right. I don't know it. I'm sorry. But
yeah.
what is big enough? Can I ask? What?
No, big enough is 5 layers.
Thank you.
That's all there is.
Okay. Any more questions? If not, let's thank Judit again.
Thank you.